We'll discuss graphing logarithmic functions and their transformations, and also finding the domain of logarithmic functions. So let's start with graphing a logarithmic function. So let's first start by talking about the parent function and some important information about logarithmic functions. Okay, so a logarithmic function is the inverse of an exponential function. So we discussed this before. So when we look at an exponential function, let's say we have f of x equaling 10 to the x power. Some things that we know. We know that this graph will pass through the point 0, 1, because 10 to the 0 power would give us 1. We also know it would pass through the point 1, 10, because if we raise 10 to the first power, that would give us 10. We also know that it has a horizontal asymptote at y equals 0. That means the graph approaches 0, but never goes through 0. When we look at a logarithmic function, so we'll take log of x, and remember that's understood to be base 10, even though it's not shown, so I'm going to write it anyway. So now, since these are inverses, remember x and y switch places. So it wouldn't go through the point 0, 1, it would go through the point 1, 0. It would also go through the point 10, 1. Instead of having a horizontal asymptote, it would have a vertical asymptote at x equals 0. And I'll show you that on the graph now. So let's go ahead and graph the parent function, the log of x. So we'll take this information we just got. So a horizontal asymptote means that the graph will not go beyond x equals 0. So it won't go to the left of or touch our y-axis. It will go through the point 1, 0, and will also go through the point 10, 1. So we know the shape of our graph, and we know some of the important values that the graph passes through. So again, the graph comes close as the y values get smaller. The graph approaches our y-axis but doesn't touch it. And our graph, as we move further right, gets bigger and bigger. Okay, so now let's graph the log of x plus 3. Let's go back to the concept of transformations. So what does this do? We're not adding x and 3. We're adding 3 to log of x. So here's the difference. If I had log of the quantity x plus 3, then this would deal with a horizontal shift. Since we have the log of x plus 3, we're adding 3 to our function, which is a vertical shift up 3 units. So all this is going to do is shift our points up 3 units. So instead of the graph going through at 1, 0, we're going to move that point up 3 units, and it's going to go through the point 1, 3. Instead of the graph going through the point 10, 1, it's going to go through the point 10, 4. So again, we have the same shape. It approaches our y-axis but never crosses. This doesn't flatten out. This is a curve at this point and continues to increase over time. Okay, so let's look at the next example. Here we have g of x equaling log of the quantity x minus 2. So again, here's the difference. Since the x minus 2 is inside parentheses, we're going to have a horizontal shift to the right by 2 units. So again, let's look at our parent function. So as if we're graphing just the log of x, so we know it goes through the point 1, 0 and the point 10, 1. And we can find other points as well. But using these 2 points as a reference, because we do know the general shape of our graph, what's going to happen is our graph is going to shift to the right 2 units. That means our vertical asymptote, which is our y-axis at this point, is going to move over 2 places to the right. So our graph doesn't go through the point 1, 0, it'll go through the point 3, 0. It won't go through the point 10, 1, it will go through the point 13, 1. So you notice our entire graph just shifts 2 units to the right. Okay, now let's find the domain. So the domain, no matter what the base of the log is found by setting the argument greater than 0. What is the argument? In this case, the argument is x minus 3. So we set x minus 3 to be greater than 0 and solve. So we're going to add 3 to both sides. So x has to be greater than 3. And if we're going to express this in interval notation, we'll go and put in our boundary 3. The values that are greater go to the right. And since it's greater than and not greater than or equal to, we'd have a parenthesis at our endpoint. So in interval notation, the point furthest left is 3. The graph continues indefinitely to the right, so through infinity. And both of these would have parentheses. Our next, we're going to find the domain of the natural log of the quantity 2 minus x. So remember, natural log is really log base e, so we're still talking about logarithms. So we're going to set our argument, the 2 minus x, to be greater than 0. So we'll subtract 2 from both sides, and this gives us the opposite of x is greater than negative 2. And then you're going to divide by a negative 1, keeping in mind when you divide by a negative, the direction of the inequality symbol changes, and a negative divided by a negative is a positive. So I'll put my endpoint on the graph, and it says the values of x are less than, so that means they'll be to the left of my endpoint. Since my inequality symbol is just less than, I use parentheses. And now writing it in interval notation, the point furthest left, since the graph continues indefinitely in the direction of infinity, that would be negative infinity. The point furthest right is a 2, and both of these would also have parentheses around them. The next example is a little bit more complicated. So here we have log base 6 of the quantity x squared minus 3x minus 4. So what we have to do is factor. So we'd have log base 6, use your shortcut of factoring. So we're looking for the factors of negative 4 that add to a negative 3. So that'd be a negative 4 and a positive 1. So remember, our argument, the x minus 4 times the x plus 1, has to be positive. So what we're going to do is we're going to set up our number line and put in our endpoints. So how do we find our endpoints? We set each one to 0. So my first endpoint would be at +4. And my second endpoint would be at -1. So we're going to look at 3 different regions. One region, we're going to look at the values that are less than -1. We're going to look at the values that are in between -1 and 4. And we're going to look at the values that are greater than 4. Now remember, we're interested in the product being positive. So when we plug in any of these values into our argument, the product has to be positive. So what we're going to do is use test points. So I'm going to choose a value less than -1. You could choose anything you want. I'm going to choose -2. I need to choose a value between -1 and 4, and the easiest one there would be 0. And then I'm going to choose any value greater than 4, and I'm going to use 5. So one at a time, I'm going to plug these values in to my arguments to see which will give me a product that is positive. So I'll start with x minus 4 times x plus 1. I'll plug -2 in for x. So this gives me -2 minus 4 and -2 plus 1. So -2 minus 4 is -6, and -2 plus 1 is -1. A -6 times a -1 gives me a +6. Since my answer is positive, this would be a part of my solution. So I'm going to just write yes. Next, I'm going to substitute 0 in. So I would have 0 minus 4 and 0 plus 1, plugging it in again to my original argument. So 0 minus 4 is -4. 0 plus 1 is +1. A -4 times a +1 gives me a negative. I can't have a negative. So that middle interval cannot be a part of my answer. And last, I'm going to take my argument, the x minus 4 and the x plus 1, and substitute my last test point, which is 5. So 5 minus 4 and 5 plus 1. 5 minus 4 is 1. 5 plus 1 is 6. 1 times 6 is +6. So since I got a positive answer, this last interval would be a part of my answer. So my answers are the intervals that made my solution positive. So my endpoints are -1 and 4. So my first interval would go from -infinity to -1. So that's where it was yes. Since I have a second interval that worked, I'm going to use union. So the middle interval didn't work, but my last interval does. So that goes from 4 to infinity. So my solution would be -infinity to -1, union with 4 to +infinity. My last example, remember that my argument has to be positive. So here I have x minus 5 squared has to be greater than 0. So keep in mind, when I'm squaring a number, if I square a positive, I get a number that's greater than 0. If I square a negative, I still get an answer greater than 0. So all real numbers would work in making it greater than 0 with one exception. And that exception would be the number 5. Because x minus 5, if I set that equal to 0, then 5 wouldn't work. Because if I plugged 5 in, that makes my argument 0. And remember, your argument has to be greater than 0. So On a number line, anything would work with the exception of 5. So anything to the left of 5 and anything to the right. So anything from negative infinity to 5 would work, as well as any value from 5 to infinity.